Hello, I'm Álvaro Calafell, and this is the first part about the impact of harmonics in electrical installations. In this video, I will explain the impact of harmonics in capacitors. Harmonics can produce different issues in electrical installations, and this video presents their influence in capacitors. Harmonics may produce an overloading of capacitors because the harmonic currents going through these capacitors depend on the harmonic voltages and the harmonic reactance of the capacitor, which decrease with the harmonic order of the voltages. These harmonic currents flowing through the capacitor bank directly depend on the harmonic voltage distortion and the harmonic order. These harmonic currents increase the root mean square value of the harmonic of the capacitor current. If the supply voltage doesn't contain harmonics, the root mean square value of the capacitor current is equal to the fundamental current, while if the supply voltage contains harmonics, the capacitor current depends on the fundamental current multiplied by a factor which depends on the square of the harmonic order and the harmonic voltage distortion. The greater the harmonic voltage distortion, the greater the capacitor current, which may produce an overload of the capacitor banks. Harmonics can also produce an increase of capacitor power losses. The equivalent circuit of a capacitor has a resistance of high value connected in parallel with the capacitor. The losses in this resistance are the sum of the harmonic voltages squared divided by the resistance. By using the loss tangent of the capacitor, we can observe that the losses in this capacitor depend on the harmonic component of the supply voltage. Broadly speaking, the loss tangent is small because the resistance is high. Thus, the losses in the capacitor are also small. The third effect on capacitors related to harmonics is the resonance phenomenon. Imagine that we have a capacitor bank to compensate the reactive power of an electrical installation, and that there is a nonlinear load connected in this installation. If we want to calculate the harmonic voltage distortion at the nonlinear load terminals by means of the approach presented in the previous videos, we must work with the following harmonic equivalent circuit. The harmonic voltages are equal to the equivalent impedance of the parallel between the grid and the capacitor reactances, by the harmonic currents consumed by the nonlinear load. We can observe that for this harmonic, the denominator of the equivalent impedance becomes 0, and then the equivalent impedance becomes infinite at this harmonic. So, at this harmonic, the value of the harmonic voltages is also infinite. We have a parallel resonance phenomenon at this harmonic, which is related to a maximum of the equivalent impedance and may produce high values of the harmonic voltages. These high values may increase the harmonic overloading and power losses of the capacitors. The harmonic of this resonance can also be calculated from the short circuit power of the grid and the reactive power of the capacitor bank. The resonance frequency can be determined from this harmonic and the fundamental frequency of the installation. As an example, we have a nonlinear load and the capacitor bank fed by a sinusoidal grid, and we are going to calculate the harmonic voltage at the nonlinear load terminals and study the resonance phenomenon. According to the videos about harmonic problem resolution, we will divide the study in the fundamental and harmonic circuits. For the fundamental, we will determine the voltage at the nonlinear load terminals by approximating to the supply voltage, the fundamental current consumed by the nonlinear load, and the reactance of the capacitor bank from its reactive power consumption. For the harmonics, we have this harmonic equivalent circuit, and first we will determine the harmonic currents of the nonlinear load from the harmonic current spectrum and the fundamental current. We will then multiply the equivalent impedance of the parallel between the reactance of the grid and the reactance of the capacitor by the harmonic currents consumed by the nonlinear loads to obtain the harmonic voltages. We can observe that these harmonic voltages or the corresponding individual harmonic voltage distortion present a high value at the fifth harmonic. This is due to a parallel resonance produced between the grid and the reactance of the capacitor at the frequency of 288 Hz. The increase of these harmonic voltages due to this resonance at the fifth harmonic may produce the overloading and the overheating problems in the capacitor bank.